Okay, so welcome Didier. Didier is not a alien face to us, and in fact, we used to joke whenever he comes to Pilani that okay, welcome back to home. So
yes, my second home. Yes.
Yeah, so we recognize Pilani as your home. And I think you might, you have traveled, I counted maybe 7 times you have visited to Pilani, and you spent more than 1 year if you count all together
Yes.
in Pilani. So, BITS Pilani is not is not a new word for you, and Didier is also not a new word for us. So I will not go with this custom to introduce BITS Pilani and so on and so on. Straightforward, I invite Didier Sebiu for the talk. I would like to thank Didier for accepting our proposal for accepting this online talk. So we are thankful for that. So I invite Didier to take over the floor and proceed for the talk.
Okay, thank you very much, Rakesh. Thank you everybody for joining. It's good to see your faces again because unfortunately last year I couldn't come. I do hope to come towards the end of this year, the situation permitting. So I'll try to now to launch my talk. Let me know, Rakesh, if you see my my talk.
Yeah, we can see.
Okay, so I will talk about something which I didn't know, let's say, a year ago, which is the memory function approach, which I have nicknamed the Swiss Army knife of statistical physics. I came across it while doing some bibliography on the way on different ways to model dielectric function, and I found that this is a very powerful and versatile and flexible method that can be used for many things. So after the introduction, I will give some mathematical preliminaries to introduce the method, then the method itself, and I will talk in particular at the end about the code we've been writing with Aditi, and the conclusion and perspectives. So this is part of the work on Plasmon, which is being done in collaboration with, on the theoretical part, BITS Pilani, so with Rakesh and Aditi, with Takashi Fujikawa and Kaori Niki at Chiba, Vladislav Kochetov, who was a former master student, who is now a PhD student in Rostock University, and my long-term friend Rino Natoli. On the experimental side, Christian Godet has done a lot on the Plasmon, and Sylvain Tri is working on both sides, actually. In Bahia, in Brazil, Denis David and Victor da Silva have worked on this stuff, and there is the group of Sudipta Barman in Indore. In addition, there have been several master students, both in Rennes and Pilani, which have worked on this over the last 2 years. On projects. So for those of you who don't know what is a Swiss Army knife, this is an example which I took on the internet. So it's I would call it an all-purpose tool, and I think it describes very well this memory function. So the founding fathers, it's Mori and Swansik who built the memory function framework upon the upon Kubo's non-equilibrium statistical physics. Sometimes in the literature, the memory function approach is called the Moritzon projection method. So Plasmon, just a short reminder, Plasmon are boson-like collective excitations. So they are the collective response of the system to the sudden appearance of a charge, a disturbance in the system. So that can be a core hole, traveling electron, etc. Therefore, they must be related to the dielectric function of the system. And this is clearly seen in photoemission, but in other spectroscopies as well, like electron energy loss spectroscopy. So on the left-hand side, you've got some experiments done by Christian Godet Victor da Silva and Denis David on aluminium. So you've got the aluminium 2s peak, and you've got the first plasmon peak, bulk plasmon, and surface plasmon. On the right-hand side, you've got the beautiful Hashcraft experiment that Sudipta Barman did in Berlin, where you can see, in addition to the at 0 to the core level peak, you can see up to 14 different plasmons that appear, regularly spaced because the plasmon frequency is constant. In order to describe this type of spectroscopies, to describe the plasmon peaks in these spectroscopies, we need to describe the dielectric function, which is the response of the material to a perturbation. And actually, the excitation of the plasmon by a charge, a core hole, an electron, is done through the so-called fluctuation potential, which is obviously related to the dielectric function. Actually, it is related, as you can see on the formula, it is related to the inverse of the first derivative, of the inverse of the dielectric function taken at the plasmon frequency omega q, at the plasmon dispersion. So this plasmon dispersion can be obtained from the dielectric function as by making the real part of epsilon equal to 0. Therefore, we deduce from this that we can generate the excitation potentials for the plasmon from model dielectric functions or from dielectric functions imported from ab initio code. Actually, this is in principle, because in practice, we've not been able so far to find an ab initio code that could suit our requirements, because in most ab initio codes, dielectric functions are calculated for the purpose of optical properties. That means that Q equal to 0. But we do need the momentum of the plasmon in the calculation, because, for instance, energy electron loss spectroscopy can measure the momentum of the plasma. So, before going further, let me introduce the family of the dielectric functions, so different functions that are related to the dielectric function. So the response function here, chi, which is related by this formula to the dielectric function. The conductivity, the polarizability, I will not use them in my talk. I will use the response function and the structure factor, which is proportional to the so-called loss function, which is the imaginary part of the inverse of the dielectric function. So these are the two quantities that we will use. In addition, we will use a constant number density. We will use a homogeneous system. So here are some examples. The well-known random phase approximation, which corresponds to the homogeneous non-interacting electron gas. So here you've got at the top the real part, at the bottom the imaginary part, and on the left-hand side is the so-called Mermin dielectric function, which, in addition to doing what the RPA does, introduces some damping through relaxation time, which here has been set to 5 femtoseconds. So you see that the big difference between the two is essentially on the imaginary part, because here on the imaginary part, you've got two parabola, which in between, this is the so-called electron-hole pair continuum, or the Landau continuum. And you see that this is where in the RPA losses appear, while for the Mermin function, you see that you have some damping outside this area, which is important for us, because you see along this dashed line, which is the plasmon energy dispersion, in the dielectric function, there is no loss here, which is unphysical. And in the middle, you've got another approach, which I will mention in a moment, the Nevanlina approach, which has the advantage to take into account correlation, while RPA and Mermin do not take electron correlation into account. And you see that this gives us a very important difference in terms of the plasmon dispersion. Now, the method I'm going to talk about, the memory function, relies on the moments of the response function chi. So the Placement frequency is well known, probably you already know it. It's given by this formula. And the moments are the traditional definition for any function. You can build moments. So here the moment of order n. In the case of the response function, the even moments are null, are 0. And we know very well the three moments -1, 1, and 3. The first one is the compressibility sum rule. The second one ensures the conservation of the number of particles. And from our point of view, the third one is very important because it introduces correlations into the system. So the Nevanlina function approach, okay, I will call it Nevanlina, but the real name is Nevanlina formula of the classical theory of the truncated hamburger moment problem. So it's very complicated. It's a purely mathematical approach, which works nice, but it's very complicated to find the corresponding function. So here is the moment reconstruction for 2 moments or 3 moments. So moment -1, 1, and 3 for the last one. And this is the reconstruction of the inverse of the dielectric function. And you see that it uses this function, the Nevanlina function, which is we still have to try to find out, and characteristic frequencies which are built in terms of the moments of the chi function, hence the importance to be able to compute these moments. In addition, omega is replaced by omega bar, which means that you can include Placement damping into this approach. So the memory function approach, which is the center of my talk, is involves the same kind of reconstruction, but it is more general. And cherry on the cake, it is connected to the dynamics of the system, which we can access through experiments. So just another example computed with the code which I will present at the end of my talk between the RPA, and here you see the dielectric function computed with the third moment Nevanlina approach using this Nevanlina function with again these omega 2 and omega 1 characteristic frequencies. So let's move to the memory function itself. So what is the idea of the memory function? The memory function methods provides a description of microscopic dynamics or relaxation of a system while taking into account microscopic unknown physical processes that can affect it. So as it deals with the dynamic of a system, it can be used in physics, in chemistry, in biology. Here I give you some sketches of time scales of various relaxation processes in nature. So the one that will concern us is essentially vibrational motion, collision, electronic dephasing, and you can go for biology to torsional dynamics of DNA. And in principle, all these relaxation processes can be treated with the memory function approach. So very briefly, the mathematical tools that we need in order to express this memory function. Well, first we have to consider what type of physical properties, what type of variables we are interested in. And this makes a distinction, a duality between what we will call the relevant variables, which are in principle slowly moving. We will call them conservative variables that can affect the macroscopic experimental signal. On the other hand, we've got all the other physical properties of the system, fast moving, which we don't know, and which we do not expect to impact the experimental signal. So the memory function method includes the effect of the irrelevant variables into the dynamics of the relevant variables. So as we've got 2 types of variables, so that means in terms of mathematics, we'll have 2 types of operators to describe them. That means that we need subspaces and projectors. So the relevant variables will generate what I will call the P space, and the irrelevant one, the Q space. And so we divide our space of variables, our space of operators, sorry, into 2 orthogonal subspaces. So once we have a space, a mathematical space, of course, we have operators, we need an inner product. Actually, we will deal with two different inner products because the method can work both in classical physics and in quantum physics. So in classical physics, it's very simple. We take for the inner product a suitable equilibrium average of these operators. In quantum physics, I will not go into details because this is pointless here, but we use the so-called Kubo product. We will need as well transforms. You will see later why. We will use Fourier transforms and Laplace transforms. They can be related in the case when you have a function, a variable which is Hermitian. There is this relation between the Fourier transform with the hat and the Laplace transform with the bar. And we have to be cautious about our definition of the Fourier transform, because you know that there are several definitions, physical, mathematical, and so on and so forth, because we will need both space Fourier transform and time Fourier transform. So the convention we use doesn't matter as long as we use the opposite convention for space and time, because normally a wave writes as kr minus omega t, so time and r have got opposite signs. This is the only thing you have to be careful about. Now, we will need time correlation functions. So time correlation functions, it's very easy. It's just the projection of a variable at time t upon another variable, or the same variable at time 0, hence the name time correlation. We can define it with the classical physics product, or we can define it with Kubo product. And if it is normalized, in that case, it's called the canonical time correlation function. An important property is that processes we will be interested in are stationary, and this has an important consequence, which will simplify a lot the memory function approach, is the fact that any operator is orthogonal to its derivative. I think it's at t equals 0, but it doesn't matter. This is only what we need. And this we will see later is very important. I come to the response function because I mentioned in the family of functions related to dielectric function, the response function. In classical physics, it is defined in terms of the Poisson bracket of the operators, and in quantum physics in terms of the commutator. And the last important part that we need is the Liouville operator, because as I said before, the memory function is concerned with the dynamics of a system, and the dynamics of a system is described by the Liouville operator, which can be expressed, Liouville operator L, which can be expressed like this in terms of the Poisson bracket in classical physics and in terms of the commutator in quantum physics. So this is more or less the end of the mathematical part. The dynamics of the system which we are interested in is described by this Liouville operator. So that means that when you integrate this equation, you obtain the dynamics of your system in terms of the exponential ILT and the value of your system at t equal to 0. So now let's go to the point of the memory function. As I said, we can consider several variables, not only one. So I will call these variables A1 to AN, and they generate the P space. So the Q space is the space orthogonal to it, where all the unknown is integrated. So the dynamics of the system, we've just seen how it can be expressed in terms of the Liouville operator. And then, because we've got if we write A of t in terms of A of 0, we've got the exponential ILT. In terms of P space and Q space, the exponential ILT can be written this is the so-called Dyson decomposition. When you do this, you end up with an equivalent formulation of the dynamics of the system, but in terms of quantities that are defined in the P space or in the Q space. This is the so-called equilibrium generalized Langevin equation. Now, let's stop a little bit at this equation, because we have here the dynamics of our system in the P space, because all variables A are in the p-space. Is a quantity which involves the collective resonance frequency matrix omega A, which is in the p-space. Here, f of t, the random force vector, which acts as a noise, it's involved q. I minus pa, it's q. So it is something acting in a q space. And in between, we've got an integral that contains A, which is in the A space, P space, and K, which is the memory function matrix, which you see involves the force autocorrelation function, which is in the Q space. So you've got here a term which is the interaction between the A space and the Q space. Now, this simplifies in the case of a single variable because, as I've told you, this is 0. So in the case of a single variables, there is no term involving collective resonance matrix, which makes things much more easy. Okay, let's take a little break and come back to things you saw probably a long time ago, which is the 1D classical particle moving in a potential. So in that case, you know that the dynamics of the system can be written in terms of the first derivative of V. In 3D, that will be the gradient. Now, this is for a single particle, a tagged particle. But in order to mimic a liquid, we need to add similar particles that will thermally move around. In that case, the dynamics, in the dynamics of the system will appear a new term, which is friction, and that slows down the particle, the friction due to the other particles moving around. And to be more accurate, we need as well to account for random kicks from the surrounding thermal bath, and this is our force, our random force. And this equation here is the so-called Langevin equation that has been used to describe Brownian motion. The random force is stochastic. That means that its average is 0. Okay, I don't discuss the rest here. I should have put it. Now let's compare the two equations. At the top, you've got the generalized Langevin equation, which is an exact equation which we derived from the Liouville equation. So it describes exactly the dynamics of the system. The second equation is the 1D particle moving inside a liquid. So what you see here is that you've got here this term with the omega A. It's the motion due to the other particles. Here you've got the same random force, and in between you've got the one that makes use of the term which connects the P space and the Q space, and they are identical if you take for the frequency, for the memory matrix, a delta function. And this is where we get the idea of Markovian and non-Markovian approximation. Markovian approximation, that means that at time t, the dynamics of your system does not depend on the previous states the system was in. So this is the Langevin equation here. Non-Markovian, and this is here, that means that at a given time t, the dynamics of your system depends of all what happened before. Okay? And so this is the big difference between the Langevin equation and the memory function equation, which is generalized Langevin equation, which is one is Markovian. It does not depend at a given time to what happened before, and the other one is non-Markovian. Okay, this is for variables, but I've introduced before correlation functions, and in the case of autocorrelation functions, we can show that the generalized Langevin equation is basically the same, except that there is no random force, which makes things much easier. So that means that now the only unknown is the memory function. But the memory function, I told you before, is an autocorrelation function of the random force. So that means that because the first equation is valid for any autocorrelation function, it is valid as well for the memory function. So that means that we can derive a hierarchy of equation for the random force. What can we apply it to? Well, we can apply it to a certain number of variables, like the number density, the charge density, spin density, to current. We can apply it to the energy, to the pressure. If you are a chemist, you can apply it to the concentration. If you are interested in the magnetic system, you can apply this to magnetization. In chemistry, to the molecular dipole, and so on. So basically, I told you we are interested to use this method for dielectric function. So there are two direct connections with the dielectric function. Is through the dynamical structure factor, because the dynamical structure factor I presented at the very beginning, it's nothing else than the time Fourier transform of the classical density-density correlation function. Or through the response function, because the response function, which I presented again at the very beginning, is nothing else than the density-density response function. So that means that in order to construct a dielectric function from this method, we need to apply it to the density. So we have Ca and Kn, which are solutions of integral differential equations. So you all know that this type of equation can be easily solved provided you go to the Laplace space. And if you go to the Laplace space, then you can write this equation, the generalized Langevin equation, like this, in terms of the memory function, the Laplace transform of the memory function. And if you take into account the hierarchy of memory functions, then you get the continued fraction expression at the bottom of the slide, which can carry on for infinity. We can do this for what we are more interested in, which is the response function, because there is a direct connection between the dielectric function and the response function. And if we do this in the case, and if we truncate at first order, second order, third order, the continued fraction expansion, we use this. We obtain these expressions where the only unknown is the memory function, because the coefficient delta can be calculated in terms of the moments of the response function chi. So what we can say is that with this formulation, the only unknown is the memory function. So in the most part, in that part of my talk, I will discuss how to compute memory functions. Well, as we have seen before, in the Markovian approximation, you take the memory function as a delta function. So the obvious first idea is to give some thickness to the delta function. And those of you who are involved in code developments, they know that delta function, you put it in the code. You have to approximate it. And these approximations are called numerical delta functions. There are many, there are at least 7 or 8 to my knowledge. I have chosen here 3 different ones. The Gaussian approximation, the Lorentzian approximation, and the sine approximation. So on the right-hand side, you've got a comparison for a given value of tau. Of course, you have to, in order to reach the delta function, you have to make it as small as possible. Here you've got a comparison between these 3 approximate delta functions, which gives us a certain number of corresponding memory functions. So we started from the Markov memory function, which gives you the standard Langevin equation, the Brownian motion equation, and we have some improvements upon this approach. Well, there are many others. I will not discuss them. Well, one obvious one is the decoupling approach, because you can think that after a certain level in the expansion, the memory function will not change much or will tend to 0 quickly. So this is the decoupling approach. which give you this type of expression. Of course, the method has been used a lot in classical physics to study liquids, and in particular to fit empirical models to the result of experiments. And in that case, you obtain the famous Debye model, which is just the exponential. Very often you say in physics that the relaxation is an exponential function. The call and so on, so I will not mention all of them. You've got short time, long time approximation, okay, equal decay time. So you see, there are many. One of the most original is the one based on information theory, so based on the Shannon entropy. And this method gives you a Gaussian type of memory function, but with coefficients that are related again to the moments of the memory function. Numerous others. So if you do this, so I've not listed all of them here, but you see you've got the time dependence on the memory function and the corresponding Fourier Laplace transform. And here I have plotted some of them. So the dotted one, I will come to it later towards the end of my talk. It is the classical call memory function, which I've used in some calculations to show you what it gives for the dielectric function. Now, let's make a second break. Have we overlooked something obvious? There's a Latin saying, so Latin, you know, was the language of the old Roman Empire more than 2000 years ago, that says festina lente. Festina lente, it means make haste slowly. So this is exemplified by these two images. So you've got the rabbit and the snail shell, and here you've got the turtle with the sail in order to make haste slowly. Yes, what about a computer experiment? We have not considered getting a dielectric memory function from a computer experiment. And in that case, that means molecular dynamics. So what we do in molecular dynamics, we put all the particle into the computer, we put forces, and we leave the system relax using the laws we have embedded into the computer. And people have done this. And basically, there are two sort of empirical laws that seem to be fairly common. It's the Lévesque-Verlet type and the Litchen type. And here we see, it's that molecular dynamics wants not one, but two relaxation times. So we have not considered this so far. Okay, this is all what mode coupling scheme is about. This was, if I'm not mistaken, this was devised by a guy in Germany called Goetz, and it's a framework to accommodate several relaxation times into the memory functions. You divide your memory function into a binary collision one, where the processes have a fast time decay, which we suppose we know how to model. For instance, any of the previous memory function models will do the job for this, and then the mode coupling itself. We can show that the mode coupling terms write like this, but the important point is that this quantity here, so here you've got the time dependence, and this quantity here, the coefficient here, only depends on static quantities, the C here being related to the static structure factor here. In addition, the terms here, the time-dependent terms here, they are related to the density correlation function. And I remind you that the Fourier transform of the density correlation function is the dynamical structure factor. So when you use the previous formula and you make a low k approximation, you end up with this simple formula where you've got here a static quantity and here your phi, which is related to the dynamic, well, which if you Fourier transform it will be related to the dynamical structure factor divided by the static structure factor. And of course, in practice, we will need not the t dependent memory function, but the Fourier transform, the energy dependent. So now it's time, we've got all the pieces of the puzzle. So it's time to adjust them, put them together within the frame, and to obtain the expression of the dielectric function. And here it is. So we've got the inverse of the dielectric function, which writes in terms of these memory functions. So here it is the Laplace transform. And these, again, characteristic frequencies. And maybe, I don't know if you remember when I talked about the Nevanlina method, but actually this is completely equivalent to the Nevanlina method if we make this identification. The Nevanlina function equal IQ3 of this. But there is an important but. We have the Nevanlina method is a mathematical method, and it's not, there is no clear way, there is no easy way to find Nevanlina functions. While here we have many ways to compute the memory function. And in addition, we can easily make the connection with experiments. So with this method, we can build a dielectric function with the conservation of the number of particles. This is ensured by the omega-1 moment of chi. We can incorporate pair correlations, omega-3. We can, even if we want, incorporate triplet correlations, because the omega-5 is not simple, but it can be computed with certain approximations, but it can be computed. So we have also the possibility to incorporate triplet correlations. Now, what about the conservation of momentum and energy, which are the other two physical quantities which we should take care are conserved? Because as far as I know, among the numerous model dielectric functions that you can find in the literature, there is only one that ensures conservation of the momentum and the energy. This is the so-called Adval Hashcraft model, and it's very complicated. Well, in the memory function approach, it's very easy to implement. The solution is to use the multivariable generalized Langevin equation. So far, we have used only a single variable with the density. So we take as variables the quantities we want to be conserved. So this means the density, the momentum, and the energy. Because we are dealing now with matrices, it's good to orthogonalize the variables to make the calculation simpler. So this can be done through Gram-Schmidt process. But before doing this, we can realize that the momentum is actually proportional to the longitudinal current, and that the density and the energy are already orthogonal to the longitudinal current. So that means that in practice, the only thing we have to do is to orthogonalize the energy to the orthogonalize the energy to the density. And this is done using this expression. So now we've got a nice set of variables which are orthogonalized. So I said that we have n which is orthogonal to the density which is orthogonal to the current, and this comes from the conservation of the number of particles, which is given by this continuity equation. And this is important because if we inject this continuity equation into the variable generalized Langevin equation, we end up with the fact that at t equal to 0, the first element of the force, the random force, is 0. And this is important for us because it means in practice that in our matrix, in our memory matrix, the first line and the first column will be 0. So, to make a long story short, order 3 in the continued fraction expression, we end up with this equation for the response function. where we have neglected, as it is done always in the literature, the non-diagonal terms in the memory matrix. So we just have K22 and K33. So K22 corresponding to the second variable, so this is the current, and K33 to the third variable, which is the heat, the energy. So what we have now, we have a response function and therefore a dielectric function that satisfies the conservation of the number of particles, that satisfies the conservation of the momentum, of the energy, and that incorporates pair correlations. If necessary, we can go even further. As I mentioned before, it is possible to calculate good approximations of the order 5 moment, so to incorporate triplet correlations, and there is another quantity which is conserved. It's the Boltzmann-Gibbs entropy. So we can add this as well at almost no cost. Let's compare now what we have done. First, we have done the single variable case with just the density, and then we have done the 3 variable case, density, the current, and the energy. So we see the difference here in the expressions of the response function. So we see that, okay, we still have these K22 and K2, K33. So I've given you before ways to compute some memory functions, and we see that actually the conservation of momentum and energy is contained in the omega 2, omega 2,1, and omega 2,3, omega 3,2, which in principle can be computed because it's just matrix element. I remind you of A dot. So this is an example, but in the single case. So RPA1, which I showed you at the very beginning, this is RPA plus local field corrections in order to incorporate a little bit of correlations, but still you see there is no damping outside the Landau continuum, the electron hole pair continuum. Here we've got the Nevanlina method which we used before, and here this is the memory function, third 3-moment memory function with the classical call memory function you see. So, and here again we have some damping, you see, we have some damping along the plasmon dispersion. So it's not, but of course we haven't had time yet. Oops, sorry. We haven't had time yet to test fully the code and to test all the memory functions. And in addition, in the Nevanlina and memory function approach, we haven't implemented plasmon damping, which we can do easily, but we haven't tested yet. So we see we have a large flexibility to compute more accurate dielectric function. And let's compare a little bit with experiments. So this is an experiment done by the Lemel and co-workers. This is not the imaginary part of the dielectric function, but it is the inverse of the imaginary part of the dielectric function. So here you see clearly the Landau continuum, which we find here, but you see that you've got a lot of damping outside the Landau continuum, and in particular there is damping of the plasmon. This is the white here. You see damping of the plasmon, which is not present in our calculation, which is normal because we didn't put it. But this is to show you that in practice, we must have damping along the plasmon dispersion. And the memory function approach will give us the possibility to incorporate it. Now, I've focused my talk on the dielectric function because this is what I was interested in. But of course, you can compute many other properties of a dynamic system with this method. Open coefficients, mobility coefficients, magnetic susceptibility, electrical or thermal conductivity. If you are interested in transport, you can compute transport coefficients, diffusion, friction, and viscosity. In addition, as I mentioned before, there is a relationship with some experiments. For instance, if you do Newton scattering, you will probe the density dynamical structure factor. If you do electron scattering, you will probe the charge density one. If you do light scattering, you will probe the energy one. Infrared absorption, you will probe the dipole, sorry, one, and NMR, you will probe the magnetization. So all these properties can be computed with this method. In addition, I have only linear properties that are expressed in terms of time correlation functions, but okay, you can use any other dynamic variable. The only difference is that you will have to take care of the random force, which disappears in the case of the time correlation function. Just briefly before going to the conclusion, the code we've been working on during lockdown, as you can see, everything is not tested, but we have tested already a large number of dielectric function, and memory function is just one type of them. If you are interested in optical systems, we have incorporated a lot of interaction potentials. In particular, I say this because I have a student who is going to work on the calculation of the stopping power in water, and water being a polar system. So we have introduced Meyer potential, which is for polar fluids. You can use this for standard solids like metals, semiconductors, heterostructures, but for massless fermions, neutral and polar classical fluids. So any type of confinement has been implemented, not fully tested, but implemented. You can add as well different type of damping for the plasma. We have not tested yet, but it's implemented. And you can use several energy functionals. The most famous ones, except that, as I mentioned before, that all this work is for a homogeneous system, so the density is constant. So of course, there are no gradient functions because the gradient is 0. So in brief, we can have for homogeneous system all types of confinement in the code, multi-layer structures, so you can dielectric function or other properties for heterostructures and superconductors. Plasma as well. We have planned to put external fields as well. It's not done yet completely. Well, it's done a little bit for magnetic field and temperature. There is a huge documentation, and a lot of different types of things can be calculated, such as structure factors, pair correlation functions, spectral function, damping, correlation energies, thermodynamic properties, mean free path, etc. And my colleague Sylvain Tricot has made a beautiful and flexible plotting interface in order to plot, for instance, the dielectric function and to plot just for an epsilon value or Q value. So I come to the conclusion and perspectives. So I've presented you a detailed account of the memory function theory, which allows to describe the dynamics of a set of variables while taking into account the other processes that are relaxing on a much shorter time scale, and which in principle we don't know. This is done by choosing an appropriate memory which embeds into the theoretical model the effect of these unknown variables. So applying this method to the density-density correlation function, we have seen that we can construct a dielectric function of moments. We can incorporate into it correlations and consolidate physical quantities of interest, and the method is extremely flexible. So to the best of my knowledge, this approach contains all the other model dielectric function, as particular cases, so the RPA is contained in it, local field is contained, Mermin, Adval, Hashcraft, and so on. So perspectives, well, we have a further advantage, is that we can think in advance to the best suited memory function to the problem at hand, which is not the case for Nevanlina approach. Indeed, as I mentioned, the memory function describes the relaxation of a dynamic variable. And in addition, we can often relate this to specific experiments that can shed some light onto the relaxation process. In the case of the dielectric function, this variable is the number density, and it is the oscillations, the collective oscillations of this number density due to the sudden appearance of the external charge that are the response of the system to the perturbation. So the collective response is plasmon, and therefore the relaxation process will describe the various decay channels of the plasmon. Therefore, this is the important point. If we can have some experimental insight into the time scale of the different decay channels, we can use the mode coupling method to build a realistic multi-time memory function. So can we do this? Well, thanks to Gianni Stefani's aid, gave me some documentation on the system. We can actually. So the main plasmon decay channels is the so-called Landau damping, which is the excitation of electron-hole pairs. You can excite as well bond electrons, or the plasmon can decay through phonon-assisted electron excitation. But this is a multi-step process because it's not only the plasmon. Once the plasmon is de-excited, is decayed, the equilibrium is still not there. So here is a sketch from the MSc thesis of Chapkin. You have the plasmon excitation, then there is the plasmon dephasing. That means that the electrons that what's the matter? The electrons that compose the plasmon normally they are in phase, and this is what the plasmon is about. Collective excitation of electrons in phase. Then it will be dephasing, and the so the decay, for instance, is Landau damping. So you see that it doesn't appear on the same time scale. Then of course Landau damping or the other modes of decay will generate hot carriers, electrons and holes. So after the plasmon decay, you will have the hot carrier that will relax, and after thermal dissipation, all this on different time scales. Oops, sorry, it's the other way. And there is here again a cherry on the cake. Is that there is people working in attosecond spectroscopy have measured the time delay between intrinsic and extrinsic plasmon. Time delay, you see, it's quite it's easily measurable. Here you've got the core peak. You've got the extrinsic plasmon and intrinsic. So we can play as well on the difference between different dynamics between the intrinsic and the extrinsic. So all this concerns the electronic dielectric function, but of course plasmon can interact with other quasiparticles such as phonon. So we are in the process of implementing phonon dielectric functions. So this is Anyundas from Pilani master project, and this will allow us to treat properly plasmon-phonon interaction. And here you see some calculations that were done, where here at the top you've got loss function again. So here the plasmon dispersion. Sorry, here you've got the plasmon dispersion without electron-phonon interaction, and here you've got with electron-phonon interaction. And you see that electron-phonon interaction will thicken the plasmon dispersion line. Will be a line, so there will be more damping. So that's all for me. Thank you for your attention.
Okay. Thank you very much, Didier. So now we can ask some audience for some questions. So please raise your hand if you have any doubt, and then I can pass your doubt to Didier, and Didier can answer it. Please raise your hand if you have any doubt. Yeah, Stephanie.
Yes. Hi, Didier. It was a very enjoyable lecture. Ciao.
Thank you.
I have enjoyed very much this lecture.
And I'm glad because, as I told you, we'll have to discuss this sometime.
Yeah.
The experimental side, what can be done.
Yeah. And I'm sorry jumping in front of all the students with my question, but unfortunately, in a quarter of an hour, I have to leave. So that's
okay.
Why. So just excuse me, all the other in the audience. Let's see. I have two questions. The first one is, this is a very intriguing method, the one you have presented. is it possible to apply also to elastic scattering? And I see what I have in mind. Is there any hope to have a method that will describe all at the same time diffraction from a lattice and energy losses?
That's a good question. I was not thinking of this when you mentioned elastic scattering. I was thinking of something else we have started to work on. Actually, it's Reno, which is to take into account the time delay between the incoming beam and the scattered beam.
Yeah, that's another very interesting one.
That's another question, and I'm eager to see what it gives, because now it's implemented in the code, but we haven't had time to test it yet.
Yeah.
Well, I have no idea for the moment. What I know is that this method is extremely powerful. Actually, I was amazed when I discovered it, and it can be used for a number of systems. So in the case you mentioned between action and well, I have no idea for the moment. We'll have to think about it.
Yeah, we will see in the future. Future will be a nice occasion to sit together and discuss over a cup of coffee. And just then I will be quiet. A second question is, suppose that you have a chain of Markovian events, right? So it means the following event is going to be determined by the previous one, and so on and so forth. Is that correct?
Yeah. Non-Markovian.
Non-Markovian, sorry, non-Markovian. So, but if I go a step further and make a complication, I mean, can I take into account interference between the different steps of these multiple scattering events? Because
yes, I guess it can be not easily done, but actually the mode coupling is very complex but very powerful as well. What I've shown is really the simple approach, but you can go much beyond, and you can mix effectively. I believe you can mix different processes inside the mode coupling.
Okay.
I will send you my extended notes on this, because I didn't want to go into this. I just wanted to make the point that when several relaxation times, which normally should be the case for the systems, the dynamics we are interested in, then this approach allows to introduce it nicely into the memory function. But of course, what I showed is a very simplified approach to the mode coupling method. Actually, there is a whole book written by Gibbs on the mode coupling approach.
Okay.
But I'm sure that what you say can be tackled with the mode coupling approach within the memory function.
Okay. I hope we'll have soon an occasion to discuss together this.
Yeah. Well, next week I didn't do it because I told you after your talk that I will contact you, but then I started to work on my presentation. But next week I will be fine. So just send me an invitation for any day, and
Good. I will do. So, as promised, I'm going to be quiet now, and I say hello, everybody.
Thanks for your questions.
Ciao.
Ciao, Gianni.
Okay. Anybody else? It appears to me that there are no more questions from the audience. So again, I would like to thank you for your nice talk, and the perspective is interesting. It can be applied to many other fields, so that can be explored.
Yeah, this is the beauty of this method. It's that it can be used in chemistry, biology. You can use study the DNA vibrations. You can study the evolution of the concentration of your system.
So you want to say anything else, Didier, before we disperse?
Just that for the students who are interested, when I am in Pilani next time, so hopefully in October, November, if they are interested, we can discuss further, and I can give more details on the question, on the matter.
Okay. Anybody else from the audience wants to say something? Yes, Subhasis.
Yeah, sorry, Didier, it's not a question, just to say hello. And that time I was without microphone. But I was surprised to look you. Like I couldn't recognize initially that it's you with long hair and all these things.
Yes, that's me.
Okay, we are also passing through very hard time here. But be safe and healthy, and our best wishes to your family also.
Okay, thanks.
Yes, Keske.
Yes, so, well, it is really very nice, interesting topic. And I'd like to know, for example, what is the limitation of this method for this, I think, third moment approximation. I mean, for time or energy or whatever, how to say. I think you introduced also a stationary approximation, right?
Yeah.
So what is, how to say, limitation? I mean, so which is a more appropriate application for?
Well, the limitation I don't know yet. Well, one which I have in mind, and but I would like to know is because, okay, so far what we have done up to the moment of order 3, I should say, it looks definitely an improvement over the standard ways. But of course, it seems to me, as far as I know, that nobody's been further. Nobody's taken into account the 5th moment. That means triplet correlations. And although the equation for the triplet correlations runs over three lines, I say, it can be computed, especially using the curve approximation, which expresses triplet correlations in terms of pair correlations, of products and of linear combination of pair correlations. And this is one of the very first things I want to test, to see if the incorporation of triplet correlations makes it, or if we have reached more or less the convergence.
I have another question. So you showed, okay, you said triplet, let's say, triplet, including triplet moment is really, let's say, more precise way. But if we use just single moment, up to single moment, what happens? I mean, what is the difference? Maybe you showed me, but I didn't.
No, I didn't show it. I didn't show it. If you use only 2 moments, so -1 and 1, it doesn't give good results. And in particular, you don't get the right plasma dispersion. So you need the third, the omega-3 moment, even without taking into account the correlation, because you can set to 0 the correlation term into the omega-3 moment. And if you do this, you will get something very similar to RPA. But you need 3 moments.
I see.
2 moments, it doesn't work properly. You need
I
the
see.
information, even without the correlation, you need part of the information on the omega-3 moment in order to get the same level of agreement as the other methods.
I think probably
So basically, that
difficult,
means that yeah,
be difficult to say, but I would like to know what is the meaning of physics, including this omega-3. I mean, physically, from this only 2 moments to third moments. I mean, namely, probably, I don't know, we include some correlations, or I don't know.
Yeah, but even the third moment without correlation gives you something reasonable.
So
correlation is important, but 2 moments is not reasonable at all. It's not
I see.
good at all.
Okay.
But 3 moments, even if you set to 0 the correlation term, in that case you get something like the RPA or the Mermin.
Yeah, you said
which gives you a reasonable plasmon dispersion.
Mm-hmm. Okay.
But you need the third one. And this is why, because there is such a big difference between including just 2 moments that I'm eager to check what is the effect of the 4th moment, which nobody's done to my knowledge, but at least on the dielectric function. But it's feasible, we will do it.
And I think computational, let's say, cost is not so huge, right?
No, it's just a matter of seconds.
I see. Yeah. Okay. Okay. Thank you. Thanks a lot.
Thanks, Keisuke.
Yes. Anybody else? Okay. Nobody is there. So again, I would like to thank on behalf of the department that you accepted the invitation and you delivered such an illuminating and nice talk. And of course, we would be very happy to see you physically in Pilani, but
yeah, me too.
Unfortunately, it couldn't be because of the present pandemic situation.
Yeah.
Hope that
I miss all the Pilani.
Yeah, hope that we will have some interaction physically, maybe at the end of this year, if situation improves. So we would be happy to welcome you, and please be safe and stay home. For us, at least we have to stay at home, and we have been staying at home for last 3 weeks because of the containment zones.
Yeah.
Hope we will have a better time and we will have a physical meeting.
Let's hope very soon we can be together.
So
okay, all the best to everybody.
Yeah. So with this we can disperse. Thank you very much.
Okay. Thanks, Rakesh. Thanks, everybody.
Thanks.
Ciao.
Ciao.